Hi, today we are looking at curve sketching using what we've learned so far. So with curve sketching of polynomial functions, we first want to find our first derivative, then we will find our second derivative. With each of those, we'll find critical points and points of inflection. We're then going to combine our line graphs that we did for both critical functions and points of inflections into a single diagram that shows our critical points, extreme values, concavity, and points of inflection. We'll then use those to sketch our graph. So for example, sketch the graph of a function y equals x cubed minus 6x squared plus 9x minus 1. Label all relative extrema, points of inflection, y-intercept. Now the easiest one here is obviously going to be our y-intercept because our y-intercept is just a constant term of original function. So we know our y-intercept already. We know that that is going to be 0, -1. So we know that we will be at that point there. The rest of it will be a bit more challenging. So first derivative of this would be 3x squared minus 12x plus 9. So look for where that equals 0. So I'll start by factoring this. So we can factor a 3 out of all these terms. So we've got y prime equals 3 times x squared minus 4x plus 3. We'll then factor that. So we've got 3 times x minus 3 times x minus 1. So we know we have critical points at x equals 1 and 3. Now we'll look at our second derivative. So that's going to, we'll take this equation up here, take the derivative of it, so that gives us 6x minus 12. Now if we factor this, we have 6 times x minus 2. So that tells me we have a point of inflection at x equals 2. Now what we're going to do is create a line graph that has all of these in it. We'll also add a few more details than last time because we'll include more information than we did last couple times. So we know this is 1, this is 2, this is 3. So far very similar to last time. What's different is we will add in some titles on the side. So we're going to have y prime, y double prime, and y. Now we'll fill in the information we already know. So we know y prime is 0 when x equals 1 and 3. We know y double prime is 0 when x equals 2. We are then going to look at our equations and figure out in our intervals where things are positive or negative. So for example, y prime, we know we can substitute an x value of 0 in for that. So if I put 0 in for y prime, and let's say fill in that equation, that'd give me a value of 9. So that would give us a positive in that interval. Where if I say substitute something in between, anywhere between these two, because those would be our two critical points. Let's say I substitute 2 in. But okay, in this equation, I have 3, which is a positive, times 2 minus 3, so that's a negative. So positive times a negative is a negative, times what would become a positive. So that would be a negative. So we know that in this interval, all these are negative. And then choose a point like 4. If I was to plug 4 in for these, I have a positive times what would be a positive times what would be a positive. So therefore, we know we got a positive value. Do the same thing with intervals here. So once again, I could probably use 0 for this one because it's to the left of this 2. If I plug 0 in, that gives me negative 12. So we know everything to the left of this 2 would be negative. If I was to say substitute 3 in for this critical point, that gives me 6 times 3 minus 2. So we have a positive times a positive, so that should give us positive. What we'll do next is figure out what our actual y values are at 1 and 3. So I'll just rewrite our equation down here. So we had y equals x cubed minus 6x squared plus 9x minus 1. So we want to evaluate it at 1, 2, and 3. So y when we're at 1 is 1 cubed minus 6 times 1 squared plus 9 times 1 minus 1. And that should give us 3. So at 1, y has a value of 3. Next we'll do 2. So when y is 2, we have 2 cubed minus 6 times 2 squared plus 9 times 2 minus 1. And that gives us 1. So at 2, we're at 1. Next, we've got 3. So we've got y of 3 is 3 cubed minus 6 times 3 squared plus 6 times, or sorry, plus 9 times 3 minus 1 gives us negative 1. So we know that's negative 1. What we'll do in these other points where we have not figured out values is look at what's happening with our graphs. So if we have a first derivative that's positive, that means that we have a slope that is going upwards. However, our second derivative is negative, so that means that that slope is going to be decreasing. So we should expect our graph in this interval to have a shape something like this arrow I've drawn it. We'll do the same thing here. So this shows us having a graph that's negative slope, and it's becoming more negative because our y double prime is negative. So that means we should end up with something that's going downwards. Here, we have a slope that's going downwards, but it's becoming positive. So therefore, this section, our graph should have a shape like this. Here we have positive and a positive, so it should start positive and become more positive, so something like this. Now, when we graph this, we're going to see if that matches up with what our points are telling us. So we already plotted our y-intercept. We know at 1 we're at 3, 2 we're at 1, 3 we are at negative 1. Now we should note that because there's a change sign here, we know this was a point of inflection. And we could tell because this was a critical uh, point and this was negative, we had a local max here. And this was a critical point and positive, so this was a local min. And if we start to the left of our first point, we should be going something like this. So we should have something that's going up, curving to right. Then we'll see we're curving down. And then we're curving it to right. And then up. So our graph should look something like this. Okay, next example. Want to sketch for graph of a function y equals x times x minus 3 cubed. Label all relative extrema, points of inflection, y-intercept. Okay, so we'll start by taking our first derivative. So y prime is equal to, we've got our product rule here, so derivative of first term, which is 1 times our second term, so times x minus 3 cubed, plus our first term times the derivative of a second, so times 3 times x minus 3 squared. We'll just rewrite this a bit, so we've got y prime equals x minus 3 cubed plus 3x times x minus 3 squared. Now, what we can see is both terms have x minus 3 in it. Our lowest exponent row is 2, so we'll factor that out of both terms. So that gives us x minus 3 squared times, that leaves us with an x minus 3 here, and a plus 3x here. Now, because this wasn't squared, technically we can get rid of those extra brackets and just combine our like terms in here. So we've got y prime is equal to x minus 3 squared times 4x minus 3. Now from this, we can see that we have critical points at x equals 3 and 3/4. We'll then take our second derivative. So that'd be derivative of this first one. So 2 times x minus 3 times 4x minus 3 plus this first term times the derivative of the second term. So I'll just rewrite that briefly. So y double prime is equal to 2 times x minus 3 times 4x minus 3 plus 4 times x minus 3 squared. Now, once again, both terms have x minus 3 in them, so we'll factor that out. We can also factor a 2 out of both those terms. That leaves us a 4x minus 3 plus 2 times x minus 3 squared. Or sorry, not squared, we already factored one of those out. So we'll go through and simplify this. So y double prime is equal to 2 times x minus 3 times 4x minus 3 plus 2x minus 6. That gives us y double prime is equal to 2 times x minus 3 times 6x minus 9. We can factor a 3 out, so y double prime is equal to 2 times x minus 3. Actually, sorry, I just said we could factor 3 out both those, so we'll factor out multiply by the 2 in front, so that gives us 6 times x minus 3 times 2x minus 3. So we can say we have points of inflection at x equals 3 and 3 over 2. Now, just like last time, we'll come up with a number line. So we had 3 main points. So we had 3/4, 3 over 2, and 3. These were all x values. We had y prime, y double prime, and y. So for y prime, we had critical points at 3 and 3/4, so we know those are both 0. Our y double prime was 0 when we were at 3 and 3 over 2. So I'm just going to write our first derivative and second derivative equations down here so we can quickly reference them. So we've got y prime equals x minus 3 squared times 4x minus 3. So if I was to put something in that's less than 3/4, so let's say 0, anything that goes in here is automatically going to be positive because it's going to be squared. So we're going to have a positive times something here. So if I put 0 in here, I get a negative. So positive times a negative gives us a negative. So we know this side would be negative. Now we'll put something on this side. So between 3/4 and 3, easy number between those would be 1. If I was to plug 1 in once again, it's going to give us a positive because it's squared. If I plug a 1 in for here, I get positive. So positive times a positive gives us a positive. So we are positive between those points. Now, if we go something larger, let's say 4, once again, this would give me a positive, but if I put positive in here, 4 times 4 is 16 minus 3, so positive times a positive does give us a positive. Now, if we look at our double prime, so our y double prime was equal to, when we simplified things, 6 times x minus 3 times 2x minus 3. If I was to say plug in 0, that'd give me a positive times a negative times a negative, so that will give us positive. So it should be positive everywhere to the left of this point. Now, if I put in a number that is greater than 3 over 2, but less than 3, so for example, 2, we'll see if we get positive or negative. So if I put in a 2, that gives me a positive times a negative times a positive. So positive times negative times a positive would give us a negative in that interval. And then let's say I put in, let's say 4, that give me a positive times a positive times a positive, so that gives me a positive. So right now we can, from our critical points, which were 3/4 and 3, we know we have at 3/4, this should be a relative minimum because we had a critical point and our y double prime was positive. So we know this point would be a minimum. It would be a relative minimum. First, there's not quite enough space to write it. Here we've got 0 is 0. So it doesn't really follow through with what we had in terms of maximum or minimums earlier because it's not greater than 0, not less than 0. So it's neither maximum or minimum. We'll get our y values next. So I'll just rewrite our original equation. So our original equation was y equals x times x minus 3 cubed. And we'll do a few points. We'll start from left, move right. So first thing is, from our equation, we didn't have a constant, so we didn't take that as our y-intercept. Instead, we'll have to plug in x as 0 to get our y-intercept. So if I have y and we're substituting in 0, that gives us 0 times 0 minus 3 cubed. So that gives us 0. So we have a y-intercept that is 0. Next, we have this minimum. So we've got y of 3/4 is equal to 3/4 times 3/4 minus 3 cubed. Now that gives us something that is roughly negative 8.5. Now if I did, so we know that we have a minimum at 3/4 comma negative 8.5. Next, we've got this point here, so 3/2. So if we have got y of 3/2, that would be 3/2 times 3/2 minus 3 cubed. And that gives us roughly negative 5.1. So this, because it is 0, means that this was our point of inflection. So that was at negative 5.1 for y and 3/2 for x. Next, we had another point of inflection. So that was when we are doing a y value of 3. So that would be 3 times 3 minus 3 cubed, which gives us 0. So we also know we have a point of inflection at 3 comma 0. Now we can use these once again to look at the general shape of our graph. So we were going downwards because this was negative. The positive meant that our slope was increasing, so becoming positive. So this section should look something like this. Then we had a positive slope becoming more positive, so that means it looks like this. Now, from looking at this, we can see that this would indeed be a minimum even if we didn't do our other tests, because we're going downwards and then we're going back upwards. If we look here, we have a positive slope that's becoming less positive because of that negative or second derivative, so we'd have something that looks like this. Over here, it's positive and positive, so it looks like this. Now we can see that we wouldn't have a minimum maximum here because our slope stayed positive. So we're going to plot all of our points now. So we had a y-intercept at 0. Then at 3/4, we were at 8.5. Then at 3/2, we were at, or sorry, that was at negative 8.5, not positive 8.5. I'll just erase that quickly. So at negative 8.5, then we were at 1.5 or 3/2, we're at negative 5.1. Then at 3, we were at 0. Now, if we look at our graph, we should be coming down, go through that y-intercept, be curving towards that critical point, curve back up. We have this point of inflection where we're then reversing our direction of the curve. And then it's curving back up at this point, so our graph would look something like this. Okay, one last example. We want to sketch the graph of y equals x times e to the x. I'm going to label all asymptotes relative to extrema, points of inflection, and y-intercept. So I might just quickly get our y-intercept right now. That occurs when x equals 0, so that'd be 0 times e to the 0, so our y-intercept is at 0. Okay, so next we'll take our first derivative. So y prime would be, we have to use our product rule, so derivative of x is 1 times the second term, so just e to the x, plus x times our derivative of e to the x, which is e to the x. At this point, I can factor this because both terms contain e to the x, so we've got e to x times 1 plus x. Therefore, we can say we have a critical point at x equals -1 because that's what makes this equation equal to 0. We'll then take our second derivative. So we'll go back up to this one to do our second derivative. So our derivative of e of x is e of x. Then we've got our derivative of x is 1 times the derivative times, sorry, our second term, so e to x, plus our first term times our derivative of the second term. So this is our new function. We can simplify that a bit though because that's 2e to the x plus x e to the x. We can factor an e to the x out of all terms. So this is going to give us a point of inflection when x equals -2 because that's what makes this equal to 0. Or sorry, that should be -2. Okay, so we will draw out our number line. We have just two main points on this number line. So -2 and -1. And we'll look at y prime, y double prime, and y. So y prime was 0 when x was at -1, and y double prime was 0 when x was -2. So for each of these, I will see what happens in terms of signs when I put stuff on either side. So for example, if I put -2 into, let's say, this factored form of y prime, if I put -2 into here, that's still going to be a positive because e to any power is going to be positive. So I'd have a positive times a negative. So that means everything on this side, y prime would be negative. If we look at something positive, let's say to 0, e to 0 is 1 times 1, so that would be positive. Double prime, I'll look at factored version. So once again, try something negative, like -3. So that's to the left of here. That would give us a negative out of here times a positive here, so that gives us a negative. On this side, we could go with, say, 0. If I plug 0 in, once again, that'd be 1 times 2, so that's a positive. So figure out what y is at each of these locations. So our original function was y equals x e to the x. So y of -2, we'd have -2 times e to the -2. So that'd be -2 over e squared, which is roughly -0.27. So we've got -0.27 here. Next, we've got y equals, or y of -1. So that would be -2, or sorry, that'd be -1. That's e to -1. So that'd be -1 over e. So that's roughly -0.37. So we found our critical point and our point of inflection. So our -2 was our point of inflection. So we know we have a point of inflection of -2 comma -0.27. And we know that this point was our critical point. So we had a critical point there. This was positive. So that meant that this was a local minimum. The local minimum at -1 comma -0.37. We'll look at our signs here and see what our graph is doing. So we have a graph that's going downwards. It's becoming more negative. So that should be something that looks like this. Over here, we have something already going downwards, but starting to become positive. So it will look something like this. And then we have a positive graph becoming more positive. So it'll look like this. Okay, so we're going to plot these points. Now I'm going to modify the y scale of this graph simply because we're dealing with such small values. So instead of each point vertically being 1, I'm going to say that 10 points are equal to 1. So this would be +1 up here. Well, this is -1 down here, which means that this here would be 0.5, and down here would be -0.5. And I'm just going to use the regular -10 to +10 on the x-axis. So we'll plot these points. We already have our y-intercept plotted. And then at -2, we are at negative 0.27. -1, we're at negative 0.37. So we can see we have something that comes in and turns downward. So we'll have a graph that looks something like this. We can see that once it hits that, we start losing some of that negative slope as it becomes positive. So it starts turning upwards, and then it'll turn upwards, go through that y-intercept and continue upwards.